Hello, my name is Veikka Nikander. I come from Optoelectronics Research Center, Tampere University, and I'm here to present you a NUSOT 2020 online conference presentation with a topic of Quasi-3D optimization of grid architecture for a photovoltaic converters using Solcore. Outline of this presentation will be such that we start by motivation and background, then we move to methods of the simulation tool. Then we do an optimization case study for a grid architecture for a gallium arsenide based photovoltaic converter. And lastly, we conclude by the conclusions from this work. Let's start by motivation and background. So, photovoltaic converter is a solar cell-like device which is optimized to convert a monochromatic light, such as laser light, to electrical energy. This sort of devices often operate with high illumination and also uneven illumination profiles. These devices are used in power over fiber applications where energy is transferred via optical fiber and laser light instead of a copper wiring. This application has a few advantages over copper wiring, such as galvanic and electromagnetic isolation, and also it is a spark-free energy transformation for flammable environments. Key parameter of such device is a conversion efficiency. Efficient cell is constructed from a efficient semiconductor material which has to, for example, have a efficient absorption of the photons and also a efficient charge carrier separation via internal electric field and so on. But also one key component of an efficient solar cell is a front contact grid metallization, which is laid on top of the cell. This metallization is there to aid the current flow generated in the semiconductor material to an external circuit. There is two losses which needs to be balanced. The first one is the shading losses, which comes if you have too much metallization on top of the cell. Then the light cannot go inside the cell since it is reflected from the contact material. But also if you have too little metallization in the cell, there are too high electrical losses and thus the efficiency decreases. We wanted to create a simulation tool which could optimize us the front contact grid metallization pattern of a given photovoltaic cell structure. We wanted this tool to have easy to characterize input parameters. We wanted it to be relatively fast and also transparent so we know what it is doing. And lastly, we want it to be customizable for our own needs. That is why we opt in to use a Solcore, which is a Python-based open-sourced solar cell simulation library developed by Quantum Photovoltaics Group from Imperial College London. This tool has a wide variety of modules that you can use in your own solar cell simulations, starting from parameters database, which consists of most of the common semiconductor parameters used in solar cells. It also has great optical and solar cell modules that you can choose from for your own specific simulation need. Then let's talk about the magic done in this work. From Solcore, we used a Solcore's transform matrix method for a 1D optics calculation. We also used Solcore's Poisson's drift diffusion model for the 1D current density voltage characteristic determination for the layer structure. These characteristics was fitted with double dot model fitting developed by Gao et al. The fitting parameters were then used in Solcore's Quasi-3D solver which takes into account the effects of front contour mineralization and illumination profiles. We also utilized Solcore's object-oriented structuring to manage our inputs and outputs of the simulation. As input parameters, our simulation tool takes the device layer structuring of the semiconductor layers. Then it also uses information about the front contact grid mineralization of the cell and also information about the illumination profile incident to the cell. The solver starts by determining the 1D optics of the layer structuring with the transform matrix method. Then we move to Poisson's drift diffusion model, which calculates a band diagram for a given voltage to the layer structuring, and from there we can also get a current density for the given voltage. With this we can construct a current density voltage characteristics to the layer structuring. Then we fit a double diode model function to the Poisson's drift diffusion model, and there we get the double diode model, which we can then use in a Quasi-3D solver. After this, the tool creates a illumination profile and front contact grid profile matrices for a Quasi-3D solver. These matrices are divided such that only one contact grid finger is in the one matrix, and besides it there's half of the spacing. These submatrices and double diode model is then inserted to Quasi-3D solver, which discretizes the cell relative to the illumination and grid profile matrices, such that all these subcells are connected to each other with a resistors which model the lateral current flow of the photovoltaic device. After this circuit diagram of the whole subcell is constructed, the Quasi-3D solver inserts this circuit model to a SPICE solver, which solves, for example, a current voltage characteristics of the given illumination and grid architecture profiles. After every of these submatrices have been solved with Quasi-3D solver, the current voltage characteristics are added up, and then we get a full current voltage characteristics of the photovoltaic cell. And from the current voltage characteristics we can get the maximum power point, maximum power, and from there we will get the efficiency of the given device with a given illumination profile and front contact grid profiling. We have named this model a hybrid Quasi-3D model, since it integrates three quite rigorous solar cell models to one tool. This tool is also relatively fast. Depending on the geometry of the illumination profile and grid profile, the calculation time can be from few minutes to 1 or 2 hours per one configuration. This simulation tool excels in grid architecture optimization when the illumination profile is uneven to the cell. We have used this tool for an optimization case study of a front contact grid for photovoltaic converter. We have done this simulation for two different PN and NP polarized structures. We did this optimization case study for a traditional finger grid architecture. We wanted to optimize the spacing of a fingers with a cross-section area of a 4.5 square micrometers. We did this optimization case study with three different illumination profiles. two of a supercaution top hat distributions, which are common for a multi-mode fiber output beam shape. These fibers are used often in the power over fiber applications. We also used the uniform beam as a comparison. Here we see the results done at 300 kelvins for a PN junction. As we can see, the optimal spacing is around 25 and 30 micrometers. When we go wider than that, we see a dramatic decrease in output power. This is due to the fact that the resistive losses increase in the cell and they are not compensated with the metallization. In contrary, if we go smaller than the 25 micrometers, the power also decreases, and this is due to the shading of the metallization on top of the cell. Here is the results for a MP structure. As we can see, there's quite a difference between these two results. With the NP structure, as the finger spacing starts to get wider, there is no dramatic decrease in output power. This is due to the difference in the top layers of the layer structuring. Since PN junction has a P-type material as top layers, which has a smaller majority carrier mobility, thus the electrical losses are larger in PN junction than NP junction. Here is also results done at 325 kelvins. As we can see, the finger spacing behavior stays relatively the same as a function of temperature, but we see a notable decrease in the output power, which is expected from a photovoltaic cell as temperature increases. Here are the results for optimal spacings extracted from the graphs by polynomial fit. As we can see, the NP structure has almost twice as large optimal spacing as PN structures. We also see that the uneven illumination profile decreases the optimal spacing. This comes from the effect as the illumination profile is uneven, and this yields an uneven voltage distribution across the cell, which then yields a smaller VOC, and this effect is enhanced as spacing increases, so the optimal spacing is now a bit smaller with the uneven distributions. We also see that the finger spacing decreases slightly as the temperature increases. As a conclusion, a rigorous and intuitive Solcore-based hybrid Quasi-3D model has been introduced, and it has been applied for an optimization case study of a front contact metallization of a gallium arsenide-based photovoltaic converter. We have concluded that device polarity and illumination profile has an effect for the optimal grid spacing. We have also calculated that the NP junction gets us a better yield in maximum power. We also see that the temperature affects slightly for the optimal grid spacing and more to the obtainable power of the converter. All in all, Solcore is a great example for open sourced efforts in photovoltaic simulations, and I hope to see it rise in popularity in recent years. I also wish that you are all well in these strange times, and I hope to see you next year in NUSOT 21 conference.